Good morning, everyone. I'm Mohammed Said, a PhD student at Skolkovo Institute of Science and Technology, or Skoltech, and today I'm excited to present our paper titled PolyMerge, a novel technique aimed at dynamic HD map updates leveraging polylines. The rise of autonomous vehicles has become a focal point in technological advancements, emphasizing the pivotal role of accurate high-definition or HD maps for real-time decision-making. And traditional mapping approaches have paved the way, but the complexities of autonomous driving necessitate automated techniques like SLAM algorithms. However, the data collection process involves survey cars or crowdsourcing, leading to challenges such as high costs, time-consuming data annotation, maintenance complexities, and large data sizes. Environmental changes can also invalidate these maps, and other recent research, such as Tesla's full self-driving feature, explores point-to-point navigation without pre-established HD maps, but requires extensive training data. A third approach, like vector MapNet, utilizes a convolutional neural network and a recurrent neural network to dynamically generate these maps, and the uniqueness lies in its use of polylines. Simply, a polyline is a continuous line composed of one or more connected line segments that offer geometrically simple and efficient representation for road shapes. However, despite their advantages, local vector map instances they require manual merging for cohesive global HD map. This paper addresses this gap, focusing on automated merging for seamless and accurate HD map updates. So for problem statement, this paper tackles the challenge of continuously updating HD maps for autonomous vehicles. It proposes a method to directly update road element polylines, eliminating the need for manual post-processing. And that's because despite using techniques like vector MapNet, the imperfect results lead to intersecting map parts or creating multiple polylines for the same road element. And our paper introduces a solution to automatically merge these polylines into a single coherent presentation encompassing all relevant features. Regarding related works, there are several studies that address the HD map updates. Some incrementally add feature layers using GraphSlam, others propose crowdsourced mapping and continuous point cloud map updates. However, these methods don't directly update final polylines. An alternative approach involves updating final polylines by merging them with the main map. Existing JS tools like ArcGIS or Vue.js or others offer capabilities for merging polylines, but they still require manual point modifications. Additionally, these tools don't effectively handle the precise challenge of managing overlapping or intersecting lines. So we introduce PolyMerge, an automated technique designed to address drawbacks in existing map updating methods and polyline merging tools. PolyMerge identifies and merges chains of polylines in HD maps considering their corresponding road element labels. It automates the merging process, extending primary polylines and adjusting overlapping sections with secondary polylines, and it aims for accurate and efficient HD map merging without manual point modifications. So for the pipeline, at first we employed the vector MapNet to generate the local HD maps due to its utilization of polyline-based representation rather than a dense collection of semantic pixels. The HD map generation pipeline for the vector MapNet consists of three essential components as shown in figure 1. First, a bird eye view feature extractor for mapping sensor data to canonical bird eye view behavior representation. Then a scene level map element detector that identifies and classifies all map elements by predicting element key points and their class labels. Then finally, an object level polyline generator that generates a sequence of polyline vertices for each detected map element. Then for our PolyMerge technique, first we transform the input map tokens from bird eye view representation of the ego frame to the global world frame. Then we create network graph of similar polylines to be merged, and finally, similar polylines are merged together under the correct label. So to dive in more details in our technique, we start with the first part, the ego to world transformer. We use a simple frame transformations to rotate and then translate each polyline's vertices given an ego frame to the global frame. Then a new map is created by concatenating the transformed maps. Then for the second part, the network generator, given the concatenated map, the goal of this part is to determine the subsets of polylines that needs to be merged together. The first step involves iterating through all the polylines belonging to the secondary maps, after which each polyline is examined for its proximity to all the other polylines in the concatenated map. And to decide if two polylines are close or not, we use Euclidean distances between all points in one polyline and their corresponding projections onto the other polyline. If any of the points from both polylines fall within an acceptable distance from the other polyline, indicating close proximity, the polylines are considered suitable for merging if they possess similar labels. And a crucial aspect of this part is determining the projection of a given point onto a polyline. This is accomplished by identifying the nearest line segment of the polyline to the point, which is determined by calculating the minimum distance between the point and its inline projection. If a direct projection onto the line is not possible, the closest edge serves as a projection as depicted in figure 2. And for the last part, the polyline merger, after computing the network graph, polyline merge iterates through connected graph edges representing polylines to be merged. It defines a main map polyline as a base and sequentially merges other polylines onto it, measuring each point according to one of the four possible scenarios illustrated in figure 3. And for specific road elements like pedestrian crossings, they are always quadrilaterals as shown in figure 4. So we use an optimized merging method. So in these similar quadrilaterals, they are rasterized onto a grid, forming a probability of polygon coverage from 0 to 1, and then a modified Gaussian blur function applied with full convolutional to prevent edge distortion. The representation is then extracted using a quantile threshold, like for example 0.1 for larger coverage, 0.95 for smaller coverage, and a threshold of 0.5 represents the median or an average coverage area. And finally, we use a rotated minimum bounding rectangle to represent the pedestrian crossing as a rectangle. Then for the results, to assess PolyMerge's performance, we conducted 3 experimental scenarios using new scenes dataset. In each scenario, PolyMerge technique processed 15 local HD map instances from vector mapnet, as shown in the left parts of each scenario, and generated merged maps as shown in comparison with the ground truth on the right parts. So PolyMerge demonstrates its effectiveness successfully merging multiple map instances and accurately encoding detailed geometries and directional information of map elements. So despite the overall success, there are some inaccuracies like the road borders at the lower right corner of the first scenario that stems from limitations in the vector mapnet method itself. And then we compared both VMN instances and the merged map to the ground truth data, and we used the partial curving method, PCM, to measure the difference between each pair of corresponding polylines. PCM normalizes vectors and matches the area of a subset between the two curves, allowing identification of the optimal section of the ground truth poly that corresponds to a short estimated poly. Additionally, we calculated the discrete Fourier distance, DF distance, which measures the similarity between curves while considering the location and ordering of points along the curve. The DF represents the length of the shortest leash that allows traversing both curves, similar to a man walking a dog on a leash without backtracking, for example. And the shown table presents the experimental results, comparing average metric values from 15 VMN local HD map instances in the 3 previous scenarios with those of the merged HD maps. And in general, PolyMerge preserves mean, DF, and PCM values with slight variations compared to VMN instances. Closer alignment to ground truth is observed for pedestrian crossings and boundaries, reducing maximum values. However, the dividers, they show increased values due to VMN inaccuracies and some unaccounted extra dividers merging with overlapping instances. And there is a higher PCM values. They suggest that there is a need for an additional smoothing step in future to smoothing to this increased zigzag movements in the merged polylines that results in high overall PCM area. So to address these issues, improving DMN accuracy is crucial. Future enhancements, including LiDAR scans or precise road element detection and expanding class categories beyond the current focus, are considerations for us. So in conclusion, PolyMerge, our novel technique for dynamic HD map updates, distinguishes itself by directly merging similar road element polylines using the local vector map. It utilizes a network graph construction and polyline projection, yielding an average representation with a mean offset mostly comparable to the used map instances. So specifically, we observe around 1.06 meter VF distance for pedestrian crossings, 0.60 for road dividers, and 1.22 meter for road boundaries, contrasting with around 0.98, 0.48, and 1.72 meter in VMN map instances. Our experiments affirm PolyMerge's ease of implementation and effectiveness, culminating in a comprehensive map closely mirroring ground truth. So that's all. Thanks a lot for your listening, and hopefully it was helpful for you. Thank you.